In the last video, we encountered the limit of 25 plus h squared minus 25 squared all over h, as h goes to 0. The reason this limit was important was because it represented the instantaneous velocity of our moving vehicle at the time t equals 25, with respect to the position function s of t equals t squared. At the end of the day, we reasoned that the limit was equal to 50. The purpose of this video is to explain 3 different ways of arriving at the number 50. One of the first ways we actually arrived at the number 50, if you recall, was through a table. In particular, if we think of h as a variable and define a function f of h to be 25 plus h squared minus 25 squared all over h, then we can think of f of h as the average velocity of the car over the interval from 25 to 25 plus h. By creating a table of values for small h, we can try to understand the limiting behavior as h goes to 0. In particular, in the previous video, we used the values of h that were 0.1, 0.001, 0.0001, and 0.00001, which are all very close to 0. We arrived at the corresponding values for f of h of 50.1, 50.001, 50.0001, and 50.00001, which seem to be converging to the number 50. However, it's important not to forget negative values for h. After all, the number 0 on the number line can be approached from 2 different directions, the positive direction and the negative one. The table above only investigates the limiting behavior from the positive direction, that is, as h tends to 0 from the right. So really all this table suggests so far is that the right-hand limit, or the limit as h goes to 0 from the right, is equal to 50. If we want to investigate the full limit, then we should consider the left-hand limit too, that is, the limit as h goes to 0 from a negative direction. For this, we can make a separate table of values, taking h to be very small but now negative, and we'd see that we'd get a similar column of numbers, still tending to 50. What this second table suggests then is that the left-hand limit is equal to 50 as well. Putting everything together then, the full limit, which is the double-sided limit, should be equal to 50 as well. Note that we needed to investigate the left-hand limit in order to say anything about the full limit, because the full limit is actually two-sided, in the sense that it takes into account the limiting behavior from both the left and the right. If the left-hand limit were actually different from 50, say 32 or some other number, then the full limit would fail to exist. What all of this has demonstrated so far is how to investigate limits by a table. But now let's consider a more geometric approach. After all, we could plot the values from our table on the plane and we get points along the graph of f of h. Alternatively, if we perform some algebra to the expression of f of h, we obtain that f of h is equal to 50 plus h, at least for h not equal to 0. For h equal to 0, the function is undefined, meaning that there should be a hole in its graph. What we obtain for the graph then is that it looks like the line with slope 1 and y-intercept 50, but there's a hole at this y-intercept since f isn't defined at h equals 0. From this picture, it's clear that the limit of f of h, as h approaches 0, is 50. Indeed, as we approach along the graph to the line h equals 0, the values of f tend to 50. We can approach from the right, where the values tend to 50, and from the left, where the values are still tending to 50. This means that the two-sided limit is equal to 50. But I claim that we overlooked an even easier way to see that the limit should be equal to 50. This method is an algebraic one, which comes from the algebra we did earlier, whereby we found f to be the piecewise function defined to be equal to 50 plus h for h not equal to 0. From this description of f, it's clear that f must tend to 50 as h goes to 0, because the expression 50 plus h tends to 50 as h goes to 0. This final method of performing some algebraic manipulation to the limit in order to obtain an equivalent but easier one will be extremely important in this course. In an upcoming video, we'll look at some of the different algebraic manipulations that are commonly useful when trying to evaluate different limits.